Today, we're very happy to have Professor Gregory McLaskey from Cornell University as our speaker. Greg got his bachelor degree from Cornell and both his master and PhD from UC Berkeley. He was Mendenhall postdoc at USGS Menlo Park before joining Cornell as an assistant professor in 2014. Greg's research focused on laboratory studies of earthquakes and other processes that generate seismic waves. And Greg has received numerous honors for his great contribution to the community, among which Keiaki Young Scientist Award in 2014 and also NSF Career Award. And Greg is most famous for his research on 3 meters long rock slabs on which he can simulate earthquakes that are closer to the earthquakes happening in the real world. And today he will tell us more about it. With this, I will give it all to Greg.
Thank you. Thank you for inviting me, and yeah, it's great to virtually be here. I do want to invite everybody to turn their videos on and also to interrupt with questions throughout. I'm going to try and I'm going to talk for like, I don't know, 10 or 15 minutes, 20 minutes. And then I'm going to stop periodically and ask people for questions. And then we can kind of make this a choose your own adventure talk. So if you're more interested in the seismology stuff, ask seismology questions. If you're interested in like the grooves that are generated on this sample, ask questions about that. We're also injecting water into this sample. So I would love it if this was like a little bit interactive and kind of like a discussion, and I'm happy to accommodate that. So definitely interrupt with questions. And worst case scenario, I'll just blow you off and say, well, I'll get to it later or something like that. All right, so here's this rock squeezing machine that I built. I did a postdoc at the USGS in Menlo Park, and there they have a machine where the rock is like about half the size. It's like a square with a diagonal fault cut in it, and that's the biggest machine in the world. So of course, when I got a faculty position at Cornell, I tried to build an even bigger machine, and this is a picture of it. And the questions, why do we care about a big rock? Well, it allows us to predict, or it allows us to ask some questions. And one of the questions is, how do earthquake ruptures start? Because people sort of think that maybe there's a fault has to start slipping slowly, and then when it reaches some critical length scale, it starts to go unstable and make a dynamic rupture. And people have like measured this, and the length scale is like on the order of a meter in the lab. So if you want to study this, you need to have a rock that's even bigger than a meter. So hence the big rock. But this big rock is big enough that not only can we get an earthquake to like nucleate and start, but we can actually get it to stop before it reaches the end of the sample. So now we can ask some questions like, what causes an earthquake rupture to stop, which I would argue is equally as important, if not more important. And then we also are learning about fast versus slow earthquakes. What I'll show is that we can get slow slip events and also fast dynamic ruptures on the same piece of granite, like under different circumstances. So this work can provide insights into why you might get fast or slow earthquakes and what type of seismic radiation is produced when the fault slips fast or slow. We are doing some fluid injection experiments. This is like more recent, and I don't have too many slides prepared for that, but we inject fluid in this fault and we can get this thing to make an earthquake. And so the ultimate goals are to basically better understand earthquakes and predict earthquake rupture. And then potentially also to better manage subsurface energy operations, which can produce earthquakes, sort of unintentionally or intentionally. And there's a lot of things that control these things, and I've listed a few. One is the frictional strength evolution. So friction is important, and I have a little picture here in the bottom right, which shows how we might expect friction to behave. So you might start at some initial stress level, and then as a rupture front moves through or something, you load up to some peak strength, and then it, over some finite amount of slip, the strength drops and the stress level drops down to a residual stress level. So stress conditions are super important, as I'll outline. There's properties of the wall rocks. I'm not going to get into that too much, but then also when you put fluids in the mix, you've got fluid pressure diffusion, fault permeability, things like that. All right, so I got a big machine, and I want to sort of explain how it works. Okay, so, well, actually, and I built this. I actually designed and built this myself. So here's some pictures of the steel frame that this machine is built from. I'm in an engineering department, so I kind of have to show some engineering related things. This is us lifting up these steel sheets. We put them in the lab. These are the hydraulic cylinders, these yellow things that squeeze the rock, and the steel frame is just sort of like a reaction frame. This is what the samples look like when they're out of the machine. They're 3 meters long, and they're 300 millimeters thick. So this was before we did anything with them. And then, you know, we put all the pieces together, we put the samples in the machine, and what it looks like when you sort of see an aerial view is it's basically the simplest thing I could like dream up, where basically you have two blocks, you squeeze them together, but in this case, you're squeezing them together, it's vertical in the picture, and then you shear them past each other. And this is kind of what it looks like today. There's a lot of instruments on the fault. So the red arrows show where we're applying essentially a normal stress to the fault, which is the interface between the two blocks. And then the black arrows show how we increase shear stress, and it causes this thing to kind of slip. So it just sort of slips forward. And we don't slip it backwards. When it sort of has reached its full offset of about 50 millimeters, we release the stress, pick it up with a crane, and put it back. Because the rock weighs 4,500 pounds. So everything on this machine is done with a crane. Okay, so we got a lot of sensors on this rock. And so this is really what I love about doing big rig experiments is you can have like a seismic network on your sample, and you can do seismology on this big rock in a way that's kind of similar to standard seismology. The squares are showing where we have slip sensors. These are sensors where they've got two parts, a probe that's glued to to the stationary block, which is the bottom one here, and then a target, which is glued to the moving block. And so when the fault slips, it increases the gap between the probe and the target. And so we can measure local fault slip, really slow slip, you know, on the order of nanometers per second, up to, you know, millimeters, hundreds of millimeters per second slip. So we can monitor the creep along the top surface of the sample. We also have strain gauges. I'm highlighting strain gauge pairs. So we're taking the difference of the two strain measurements to get shear strain, which we then just multiply by shear modulus to get shear stress. And it's off the fault, but it's only off the fault by about 5 millimeters. And we have an array of shear strain sensors all along the fault. We also have the black circles show piezoelectric sensors, which are essentially they're vertical ground motion sensors. So like single axis, it's your nodal array, okay? So like I said before, you know, having a big rock is cool basically because we can get this thing to slip, but instead of the entire block slipping, we can get just part of it to slip, and then the other parts of the fault don't slip. So the block kind of behaves like a caterpillar, right? So part of the fault slips, the other part doesn't. And that allows us to, you know, ask the question, well, why didn't it slip? Or why did the rupture stop where it did? And the way that I image this is those slip sensors, and I've color coded them. Red on one end, the red end is the end I'm pushing on, blue on the other end. And this is the output from those slip sensors for one slip event, just an example slip event. And so there was an event here at about 38.2 seconds. There was an event which is like a sudden increase in slip seen by a bunch of different sensors. And the blue sensor, for example, didn't see any slip at all, like maybe a little increase in noise or something. But the red sensors, the orange sensors, the yellow ones, those ones all showed some slip. And there was also some slow precursory slip on the red and orange sensors that preceded that, the dynamic part. It didn't slip much, right? It slips maximum of about 335 microns.
So I have a question. How do you make the two end sections not to slip from the experiment perspective?
So what we do is, great question, by the way. This is excellent. This is a good sign. People are asking questions. So what we do is we can sort of, there's a few tricks we can do with this block that make it so that the stress distribution down the block is non-uniform. If the stress distribution is uniform, then whenever a rupture starts, it will just blow through the entire fault. And if we just like load it up and it slips and we load it up and slips again, eventually we get into like a steady state behavior where it's just gonna, every rupture pretty much blows through the fault. But when we first squeeze the two blocks together, we first apply the normal stress. There's like frustrated Poisson expansion. The two blocks are not the same size. The boundary conditions on the block are not identical. And so we can set up a non-uniform distribution of shear stress in addition to a non-uniform distribution of normal stress. And that can cause, in this case, it caused it to promote the rupture on sort of like the first meter or so. And then the stress was unfavorable for continued rupture propagation on the last meter of this rock. Good question. So I want to introduce you this idea of what I call a pink-purple diagram, which is the same data as I'm showing here, but plotted differently. Instead of just plotting the raw output of these slip sensors in time, I'm plotting snapshots of the distribution of slip in space. So here's the 0 meters is the end we're pushing on. That's the red end of the fault. 3 meters is the blue end. And what I'm doing is I'm laying down like another sort of snapshot of the distribution of slip once every millisecond. And I'm changing the color of those contours so that every 50 milliseconds, it cycles from light pink to dark purple. So when the contours are being laid down and they're so close together because it's slipping really slowly, you can see this pink and purple color banding, and that's an indication of slow slip. And then when the individual contours separate, it's because it's slipping quite fast, and that's dynamic slip. So basically it's tuned, this plot is tuned so that when the contours separate is about a slip speed, which would be considered dynamic. So like 1 millimeter per second or so. And so it's plotting the exact same data, right? And so now you can visualize the spatial extent of that slow slipping region and the spatial extent of the final slip distribution after this event. So you can see that it really was sort of slow slipping for about a meter. And then in this case, the slip sort of accelerated out of the edge of that slow slipping region and ruptured another meter or so and made this little partial rupture event. You guys with me? Pink purple diagram, okay? So we can say, well, maybe the length here where it was slow slipping, we could call that the nucleation length, and I can label it H star or LC or something like that. And so basically in the lab, that nucleation length is about a meter. And so people think that might be the way that earthquakes begin, is that there's some slow slipping region. If we sort of move forward in time, the stress is dropping in the region where it's slipping, it's increasing a little bit on the edges of that region. Maybe that causes a stress concentration to cause the slipping region to expand a little bit. Once it reaches that critical length scale, LC here, it goes unstable and you've got dynamic rupture. And it's actually super fast, right? Much faster than I'm showing here. And there's theoretical predictions for what different parameters that nucleation length scale should depend on. It depends on shear modulus. So I was saying, like before the talk started, that I also do some experiments on plastic. Shear modulus of plastic is about 15 times smaller than on rock. So we can see that nucleation length scale shrink down about 15 times smaller. It also depends inversely on normal stress. So when we're at higher normal stress, it's a little bit smaller nucleation length scale. Larger normal stress, it wants to sort of creep more, and the nucleation length scale is bigger. It also depends on friction parameters. All right, so with this pink-purple diagram, we can basically image the beginning of one of these slip events. And so I'm going to just show, this is like the same data plotted 4 different ways. Here's a pink-purple diagram. This one's a little bit, pretty similar to what we showed before, actually, but this is a complete rupture event. So this one ruptured the entire 3 meters. I'm just zooming in on the first 10 microns of slip, and you can see that it was accelerating and it went dynamic. And then this is oftentimes modeling studies. When people that model earthquake nucleation will plot logarithmically spaced contours. That's what it would look like if we plotted logarithmic spaced contours in slip and slip rate. Slip rate's a little bit hard to deal with because of the differentiation accentuates high frequency noise. So I'm going to primarily just look at these types of pink-purple diagrams. Here's another event on the same machine, just actually moments before the other event, we got this one. So this one is creeping on that first meter. It's also creeping on the last meter of the fault. And then you can see the slip accelerates, it nucleates out of the intersection between the creeping region and the locked region. So right at about 2 meters. So we see some variation in the way these events start.
Actually, I have a question. So yeah. Are these different runs on the same apparatus or the same fault?
Yeah. Actually, the 2 I just showed you are sequential events on the same run, on the same fault. Everything is the same.
Oh, I see. That means the condition on the fault surface is modified after each event.
Yeah. So every event is going to leave a residual stress distribution that's a little bit different. And so sometimes we get some variation.
I see.
And I'll show some examples of that too. Good question. So to just show you sort of like some additional examples of what we're looking at here, if we go to 10 megapascals, the previous events were at 4 MPa. At 10 MPa, we can get a little bit smaller nucleation region. So a little less than a meter, but the same idea. Sometimes we can get completely contained events by setting up a specific stress distribution. So in this case, it nucleated at 2 meters, but it never really ruptured past, the 1 and 2.7 meter mark. It was completely confined. And then oftentimes we see this where we get some creep on part of the fault and we see nucleation right at the intersection between a creeping region and a locked region. And you can even see it's rupturing faster into the previously locked section than it is back through what was creeping. So the horizontal spacing of these lines kind of gives you an indication of rupture velocity. Now, what I'm showing you before is a one-dimensional view of what is really a two-dimensional process. This slab is 300 millimeters thick, and I was only showing you data from slip sensors on the top surface. So I did some experiments where I put slip sensors both on the top surface and on the bottom surface of the sample, but only for half of it. And so what I'm showing you here is the pink-purple diagram you would get from just using the top surface sensors or just the bottom surface sensors for the same event. And so you can see they're a little bit different. The details are different, but that length scale, a little bit less than a meter, can be imaged in either way. And on the right here, you can see like really roughly interpolated snapshots of projections on the fault plane. Like it started slipping on the bottom, and then these are contours of slip. So this is like half a micron of slip occurred. And then eventually it started slipping more on the top. And then eventually it kind of slipped both on top and bottom. And then at some point right around here, it starts to just propagate along the length of the sample. But this is just to illustrate that there's some complicated two-dimensional effects that happen. And usually the nucleation will start near a free surface, either the bottom or the top free surface. And the nucleation that we see might be the intersection of those two, sort of like when those two sort of come together, then you get a nucleation thing.
Do you measure the A minus B in a rock sample, and does that match the critical distance match the equation that you showed earlier? If you plug in the N minus B and the stress condition, does that match?
Right. Good question. So do we measure the friction parameters? We do not directly measure the friction parameters. The standard way of measuring A minus B is by driving the rock at a constant velocity, which we can't do because it's not stiff enough of system to do that. So instead what we do is we put in like what we would consider to be representative A minus B parameters or representative D sub C parameters. And the measurements that we make are to an order of magnitude consistent with this theory, okay? If you put in the normal stress, you know, we're estimating D sub C is about 1 micron. These are pretty much bare granite surfaces. The theory works, but I'm going to say to an order of magnitude, okay? And I say that because we see an order of magnitude variation in nucleation length scale under different conditions, and I'll explain those, okay? Basically, sometimes you would expect the nucleation length scale to be 2 meters, but it's tiny for some reason. And that happens due to heterogeneity, I'm going to argue. And sometimes all we have to do is just let that fault sit and heal for like a minute and then reload it. And the nucleation length scale appears to have shrunk by an order of magnitude. So state or loading velocity or healing time or whatever you want to call it also affects these things. And these are basically, these are complexities that are not, they're not captured by that equation that I showed a few slides ago. But to an order of magnitude, it does check out. All right, I'm gonna pause here to acknowledge my class.
Greg, a question. What do you mean by the nucleation phase is likely an artifact? So do you observe nucleation phase in the experiment or not?
Oh yeah. Yeah, sorry, I didn't mention this. So in a lot of previous work, especially on smaller samples, people have said like, oh, look, it starts to slip slowly and then suddenly it starts accelerating. And let's call that phase 1, phase 2, and then it dynamic ruptures or something like that. But what I'm showing here is that if you just looked at the top surface, like let's say, or just the bottom surface, you would see it's kind of slowly slipping along. And then all of a sudden it looks like it accelerates very quickly. Or if you just looked at the bottom, maybe there's a tiny, or the top, there's a tiny little bit of creep, and then it sort of noticeably speeds up and then suddenly goes dynamic. Those like sudden changes in the rate of slip acceleration are likely due to interactions with like a migrating slow slip patch interacting with the free surface of the sample. And they probably don't have a natural counterpart.
But would you still consider this first part of the slab as a nucleation or not?
Yeah, I would divide it up into 2 parts: quasi-static nucleation and dynamic rupture.
So you think there is no such thing as the quickly speed up? The quickly speed up it's a free surface effect.
Well, in laboratory experiments, it usually is.
Okay.
Now, with heterogeneity, you could have cases where, you know, things are sort of slowly slipping along. Suddenly it like has been loading a kind of stuck patch. That patch, you know, suddenly goes, things speed up very quickly, and you could get something like that.
So this slow, almost this slow sleeping stage is universal in the experiments.
Pretty much.
Okay.
Pretty much. I'll show you some examples where it's highly abbreviated.
Okay.
All right, so let's acknowledge who's doing the real work here, just to take a little break, okay? My PhD student, Huey Ke, who's co-advised between Dave Kammer and I, he's done all the work on fraction mechanics and rupture termination and stuff, and he's got a few papers out. And also, he installed all the strain gauge pairs and did a really nice job. Bill has done the work with seismology. I'll show some spectra. Bill's done all that work, and Sarah is involved in the fluid injection part which I can present a little bit if you guys are excited about that. All right, so the next thing I was going to talk about, love the questions though, by the way, keep them coming. The next thing I was going to talk about is, what does it mean to, like, what's this nucleation thing mean, for real earthquakes? Well, what is this nucleation length? And I argue that, if you take this 1 meter in a lab and you say, well, let's say the friction is the same, okay? The shear modulus is about the same, and the normal stress increases by, factor of 10 or so from our experiments. You're going to expect that this length scale is really small, like less than a meter. It's a meter in the lab. It should be a 1/10 of a meter in the earth, if these assumptions are right. And I think that that's, you could argue that this d sub c is maybe 10 times, even 100 times bigger in the field than in the lab, and that would cause you to have 1 meter, maybe 10 meter nucleation length, but it's small. So that's smaller than, that's like the size of a magnitude -2 earthquake or something. It's a small length scale. So, and I think that's probably a reasonable interpretation of what's going on in what we would call locked sections, continental faults, Eastern California shear zone, Oklahoma, places like that. We would expect a really small nucleation length. But, there's other places that don't behave the same way. Subduction zones, for example, are known to creep. There's creeping sections of mature faults like San Andreas. So if you have a section of the fault that's able to creep, that means that the nucleation length scale is large. And if your fault was velocity strengthening, the nucleation length scale would be undefined. And if it's velocity neutral, it's going to go to infinity, right? So at some point, there's going to be some faults that do have really large nucleation length scales, even if it's just at the transition between locked and creeping sections. So everybody likes to talk about foreshocks, so I'm going to just talk about foreshocks a little bit. If the nucleation length scale is small, as I suggested it probably is for continental faults, then foreshocks that you observe, they're just normal earthquakes. They had a small nucleation. Any foreshocks that you observe are probably just standard stress transfer that just happens to trigger an earthquake that was big. The other end member of how you would interpret foreshocks is this pre-slip model, which says that maybe the foreshocks are actually just a byproduct of the nucleation of a big earthquake. So maybe there's a big earthquake, and if you took some average properties over a fault, the nucleation length scale is on the order of 10 kilometers or something. But there are local sections on the fault that are a little bit more brittle, and so those things can make small earthquakes. So as this 10-kilometer section of the fault is accelerating and slow slipping and creating this nucleation process, you get some little foreshocks, like swarms of events that are an indicator of that process. And maybe that's a good way of interpreting some earthquakes that have had foreshocks in subduction zones, like the Tohoku earthquake, Iquique, and some others. So anyway, these are some ways in which nucleation length scale can matter in terms of the way you would interpret foreshocks. Now I'm going to present some evidence that, yeah, I'm a lab guy. I was all excited about the pre-slip model. We can see this nucleation length in the lab, but now there's some stuff that makes me think maybe this isn't quite right. So here I'm presenting some experiments at 2 megapascals. So remember, at 4 megapascals, we had about a 1 meter patch size. At 2 MPa, it should be like 2 meters or more. And indeed, what we see is that most of the fault will kind of creep at 2 MPa. And so that's what's shown here with these pink-purple banding. But in this case, we saw an event nucleate kind of right out of the center of the fault. And indeed, the length scale is close to 2 meters. And what I'm showing here on the upper right is if you just took the slip time history right in the center of that nucleation patch and you just plot it on a log scale, you'd see that it follows this 1 over time to instability slip time history, which is what's expected from nucleation models, like theoretical nucleation models. But then the very next event of the sequence nucleates differently, and then the one after that is even more abrupt. And what we can see here is there's one part of the fault that's kind of got stuck. So most of the fault's creeping, but this one part is stuck, and you can see that that's where dynamic rupture initiated from. Of course, this is a one-dimensional view of a 2D process, but if you had to guess what that length scale was, it's not 2 meters. It's as small as the spacing of my sensors, so like less than 0.1 meters. And additionally, if you look at the slip time history right in the center of this nucleation, you see that it started to slip, and then suddenly it started slipping really fast, like much faster than 1 over time to instability. So we're seeing a dramatic reduction in the apparent nucleation length scale just because of heterogeneity. And this is mild heterogeneity. I've got a picture of the fault, but it's like, you know, it's a plane. It's got a couple little scratches and grooves on it, but pretty much this is like as heterogeneous or as heterogeneity free as you can get or would ever expect to get in the Earth. And still we can see about an order of magnitude variation in the effective nucleation length scale. And so if I, you know, draw a cartoon to try and explain what I'm talking about, let's say there's some little bump or something. This is a projection on the fault plane, and there's a little bump that's kind of stuck. Maybe it's like a little bit more brittle or a little bit stronger than the surrounding. And there's some slow aseismic slip that starts to migrate in, and it wraps itself around that stuck patch. That can be the site of an earthquake. That's how the earthquake initiates. And I argue that that type of initiation doesn't have anything to do with some critical nucleation length scale, because now the rate of the work rate starts to matter. So, you know, Yoshi Kaneko has proposed a critical power density, and this is sort of like supporting that that idea, is that maybe earthquakes can initiate a different way. And if you try and say, well, what does that mean for these nucleation models? First of all, it means that this pre-slip model is probably not right, because if you did have small earthquakes that were a byproduct of a nucleation, those small earthquakes would probably be energetic enough that they could potentially kickstart a rupture. Maybe not, but certainly possible. And so that's what I'm trying to draw here, is that even if you had a large nucleation length scale and you had sort of like this pre-slip model going on, you might expect to see that the final dynamic rupture actually was one of those little foreshocks that just dynamically got away. And so you wouldn't expect to see any difference in the initial P wave signatures of this event, you know, from this event. There was nothing like special about it. It just happened to, you know, meet favorable conditions on the fault and just grew big. And so I think this is a way of reconciling slow slip that we see in subduction zones, but the fact that small and large earthquakes seem to initiate similarly. Okay, so just to summarize what I've talked about so far, you know, we can image the initiation process. We expect a small nucleation length scale for highly coupled faults, but heterogeneity really, it has so much influence on the nucleation length that it causes me to think that maybe nucleation length is an artifact of the super flat homogeneous surfaces that we have in the lab and in a theoretical model or numerical simulation. That when you put in real heterogeneity in the Earth, the nucleation length scale kind of becomes meaningless. So I put myself out of a job.
Can I ask a question following on this? It's,
yes, please.
Can you comment on the idea of ETS events can trigger megastressed earthquakes as being proposed and observed near Mexico subduction zone?
Yeah, I mean, why not?
Then what would be the situation to let that happen? Because ETS events happen all the time. Megathrust earthquakes don't.
Yeah, so presumably every ETS event is kind of like throwing a little bit of stress onto the locked megathrust. Okay, you're getting a little bit of slip in the adjacent adjacent region, and it's not slipping on the megathrust presumably. So stress is increasing. Eventually, that stress level on the megathrust is going to reach a critical state that it's big enough to host. The initial stress is high enough compared to its strength, perhaps, that it can host rupture. And then one of those ETS events is probably going to throw it over the edge, and it's gonna go. Not to say that that's the only way a megathrust earthquake can start, but it certainly seems possible to me. I can show you a little bit about this idea of throwing stress. Okay, so now I'm going to switch gears and start talking about termination. Now we can't ignore the initiation, but it's part of it. But how do ruptures stop is actually super interesting, I think. So let me show you a sequence of events. Before I was just sort of like showing isolated events, right? Now I'm going to show you a sequence of events that we generate right after we squeeze those two blocks together and create a heterogeneous distribution of initial stress. So we're loading up the fault, and we get this sequence of events. 1, 2, 3, 4, they're numbered, right? And this is the little pink-purple diagram for each of those individual, the first 6 events. So you can see that it started to slip at about 2 meters down the length of the fault. That's where the stress was most favorable or most critical, for rupture. But it was slow. The pink and purple lines have never separated. Then, we kept on loading it, and we got another one, and it was a little bit faster. And then number 3 looks pretty similar to number 2. Number 4, now you can start to see there's a little bit of a nucleation process going on, and then it slipped fast, and then it slowed down, and then there was a little after slip kind of on this far end. And then event number 5 looks pretty similar to number 4. And so we can kind of say, well, maybe that's the nucleation length scale. Okay. And then event 6 finally blew through the whole sample, and we can see a stress change on the sample average stress, which we're measuring in this case with hydraulic pressure sensors. And then after that, every event pretty much blows through the whole sample. So what's shown on the bottom, the bottom left here is like the approximate ruptured area of this sequence of events. And we have strain gauges on the sample. So when we see one of these events, that this is like the final slip distribution of one of these completely confined events, and now the black diamonds are showing the stress change from before that event to after that event. You can see that the stress dropped within the part that slipped, and it increased slightly on the edges of the slipped region, which is actually what you would expect from a standard crack model. It's a shear crack, it slips, and you can get to these bigger events. And so you can see, again, the stress drops. It drops about 1/10 of an MPa in the ruptured region. And then it increases outside that. And then it's got this square root decay outside of the crack. So this is what I mean by, if something slips, it drops the stress in its, right where it ruptured, but it sort of sheds the stress to the adjacent regions. And so that can kind of explain that sequence of events that I was showing before, that was getting faster and slightly bigger. So if we imagine that this black line shows an initial stress distribution that was set up by our loading procedure, and then what happens is you get an event, and that drops the stress in the ruptured region, and it increases the stress in the surrounding region. So the stress changed from black line to this light blue line. And then okay, now this is the new stress state. We continue to load the sample. It increases. It gets up to some critical stress level again, and we get another event. And so what you can hopefully see is that as this sequence of events unfolds, the stress distribution becomes less peaked. The part that had slipped before drops the stress and pushes it to the side, so you get a more uniform distribution of stress. And so you get a larger region of the fault that is stressed to a level that's above some residual stress level. In other words, you have a larger section of the fault that is favorable for dynamic rupture propagation. And if you get a case where the nucleation length scale is constant, but the section of the fault that's favorably stressed for rupture propagation is larger and larger, in other words, if your ratio of P over H star increases, you get faster and faster and more dynamic events. Until you get to this case where the stress is homogeneous enough along the whole sample that the entire interface ruptures.
So Greg, do you think this represent how in a real world a fault matures over time?
So this is kind of a contrived setup, right, that we've got in the lab. I would say fault maturity is a complex topic, which I can't get into too much, but it does talk about how different earthquakes might communicate with each other, and how you might expect to see some small earthquakes that are just sort of like evening out the regional stress field that then basically pave the way for a larger rupture to come through. So I think this type of behavior can explain some phenomena that we see in the earth, but it seems like, at least in the lab, the sample wants to tend towards evening out that stress field. So we set up an artificial stress distribution that's really inhomogeneous, and it always gets evened out. And if we just continue to load, it gets pretty homogeneous.
Thanks. And also, I think Peter has a question to ask. Peter?
Yes. It was a very interesting talk, but to kind of follow up on the question about the stress state. My understanding of a lot of recent laboratory experiments that have used rotary setups and things like that is they've shown, when you have large slip, you have a drop in the coefficient of friction, from the sort of standard lab values around 0.6 to values of 0.1 or even less. And I'm assuming that you have large values of effective coefficient of friction. I'm just wondering how you think these results may relate to the other lab results, and also the conditions in the real world.
Yeah, so great question. With this big sample, we can't access the friction like as directly as you would with a sample that you're just driving at a specific rate and measuring its resistance to sliding. But we can kind of infer it based on the way that dynamic rupture can sort of unfold. And definitely comparison to modeling is a way of helping get at that friction. We have been able to successfully model these confined ruptures using a very basic linear slip weakening friction relationship, where the coefficient of friction is like 0.6 or maybe 0.8 and drops down to 0.6 for static to dynamic friction. We do have some high-speed strain records that we're looking into to try and see if we can get, like, maybe there is some dynamic weakening that we're sort of like missing because we're not measuring it at a high enough speed. But we have a strong fault, and it's not coefficient of friction of 0.1. We don't have melt flying out of our sample. If there is a really weak phase, it's happening dynamically and it recovers very quickly. And so far, my experiments have not been able to sort of like verify that that is the case. So I would say that this rock does not support the rotary shear extreme weakening observations.
Okay, but I mean, you have not been able to do the amount of slip, I guess, that those experiments do. And I think, you know, in terms of the dynamic weakening mechanisms, the problem is, you know, when you have a very stiff sample, you know, you're not able to get at that. So I'm sort of interested in how the plastic experiments, if you're able to get closer, I guess, you know, to the regime where the dynamic weakening mechanisms might start to occur.
Yeah. Okay, great point. So first of all, the rotary shear experiments and other experiments are slipping a lot, right? So, you know, sometimes up to 1 meter of slip cumulatively. And there are weakening mechanisms that you would expect to kick in sort of like later on, maybe thermal pressurization or something where it would require a large amount of slip. We don't slip at 1 meter. Even 1 millimeter would be a lot for this machine. It will slip like 0.5 millimeter on the big ones. I have a hypothesis that weakening rate is much faster or much more aggressive with slip than the rotary shear experiments are making it out to be. Like the rotary shear experiments are often saying like, look, you really need to have like 0.5 meter or 1/10 of a meter of slip in order to get down to this low friction level. But Zev Rekis and colleagues at Oklahoma have shown that if you accelerated that fault, if they have that spinning flywheel machine where they just basically slam a fault to start accelerating really quickly, they show that the weakening occurs over much less slip. And even Zev's machine is loading the fault really, like the acceleration, the slip acceleration is sluggish compared to what we would expect a dynamic rupture of an earthquake to produce. We're talking about the difference between, I don't have the numbers off the top of my head, but it's a couple orders of magnitude higher acceleration that we can measure from a dynamic rupture front propagating down a rock than what is possible to produce with a rotary shear machine. So it's possible that a lot of that extended, like the weakening that requires an extended amount of slip is simply because they're not accelerating the fault as quickly as you would expect in the earth. So that's my thought on that. But the plastic does behave differently. When we do bare plastic on plastic samples, the thing is weak. It is very easy to get dynamic ruptures. We've injected fluid into bare plastic and shown that like even when the entire fault has sort of stick slipped and you're at a residual stress level, if you just inject fluid there, it'll slip again dynamically, even multiple times, suggesting that the dynamic coefficient of friction is far lower than the static, which would, you know, I guess you could interpret that as extreme weakening. Maybe that's because the plastic is melting. Yeah, I haven't really explored that comparison as much as I should. Those are great questions.
Thanks. I think Yuri also has a question. Yuri?
Yes, I have a question and a comment. My comment is about dynamic weakening. And I think for dynamic quickening, what really matters is the slip rate. So those effects have been observed at slip rates on the order of meters per second. Do you know how fast your samples are slipping?
Yeah, we're slipping
Maximum slip rate.
1/10 of a meter per second is kind of where we top out, I think.
Okay, so that's probably not getting into that range that is explored by the rotary shear experiments. And I have also a question about the nucleation lengths, but perhaps we should let you finish the talk, and I can wait with my question until you conclude.
Oh, okay. All right. Well, sounds good. I'll just present like a couple more things. So we've got these slow events and fast events on the same rock, right? And I'm just showing like some examples. The first three are actually from the same sequence, and then the fastest one is from a different sequence. It's at higher normal stress. And this is just showing some of the waveforms we would get out from the piezoelectric sensors going from super slow to super fast. And the original signals are in the center panels here. And we can also look at their slip distributions, and you can see that the slow events have low stress drop being basically the average slip or the peak slip divided by its rupture length or something. And since the area of the fault that's slipping is not changing much from event to event, more slip for the same area means higher static stress drop. So the fast events are high stress drop, the slow events are low stress drop. And then we can also get a source spectrum from these events we've calibrated the seismic network essentially to remove for instrument response and also the wave propagation effects. We've used an empirical Green's function calibration approach. And so we can look at the source spectrum of these slow to fast earthquakes, and we can see that the fast event is pretty well modeled by a Brune spectrum. It's got an omega squared fall off, and it's got a pretty distinct corner frequency. The slower events are showing depleted radiated energy near that corner frequency, and the corner frequency is apparently dropping to a lower corner frequency. And both those things combined cause the radiated energy to reduce by orders of magnitude. And so that's why basically for the fast event, the low frequency and the high frequency stuff are kind of coming in tandem. Looks kind of like a normal earthquake. The slower events, if you high pass filter it, you can just see like a little tremor like signal riding on top of a low frequency signal. The low frequency signal is related to quasi-static deformations because we're so close to the source. So this is a similar it's a similar behavior to what's been observed for low frequency earthquakes in the field, where they're apparently depleted next to the corner frequency. We can see an omega to the -1 fall off for the slowest events. That's similar to what's seen for some low frequency earthquakes as well. So not only are we able to generate sort of like the full spectrum of slow to fast events, maybe not as fast as Yuri would like, but they're on the weak side of a standard earthquake, but still a standard earthquake. But we're able to quantify the seismic radiation and see that there's a consistent change showing depleted energy near the corner frequency in the slowest events. And I'll end it there and take all the questions you have.
Thanks so much. And I think maybe we'll let Yuri ask his second question first.
Yes, Greg, very nice talk. So the normal stress distribution on the shear interface is highly heterogeneous, right? So we have these variations on the scales of microasperities where stresses can be as high as hundreds of megapascals, perhaps gigapascals. My question is whether you have an idea of what is the actual size of the asperity for that situation where you see this variability of your nucleation length scale. And this is related to the fact that nucleation length scale is, of course, normal stress dependent, right? So if for whatever reason you develop normal stresses that are significantly different from these nominal stresses that you apply in the far field, perhaps that same concept would still apply. And the reason why I'm thinking that is that you're seeing that at a relatively low normal stress, right? And so this means that you're not pressing on all these asperities as hard, and perhaps you're interrogating just a smaller fraction of those. So it just happens so that for that particular setting, you just had a smaller area of the fold that happened to support a much higher normal stress. Things would still be consistent with the nucleation size theory.
Yeah, great question. So here's a picture of what the fault looks like when we take it out. You can see there's some smears and scratches. So the heterogeneity that's causing that dramatic change in the way that the slip event is nucleating is pretty small, right? But I agree. So you're right. Nucleation length scale should decrease with normal stress, and obviously an order of magnitude variation in normal stress from a bump to not a bump is totally reasonable in the Earth. So maybe we should expect to see an order of magnitude variation in nucleation properties. I guess I would then say, well, if the Earth really is heterogeneous, then where do you go? Because there's probably bumps within the bumps, and if you consider like maybe the normal stress distribution is related to the topography, and the topography is fractal in some sense, then you've got a fractal nucleation length scale, which kind of makes it irrelevant.
Well, in a sense, fractal actually helps you, right? Because the reason why the coefficient of friction is constant at the sort of at a zero order, right? So if we ignore just these rate state effects, is the fact that we have a fractal surface. And so we have these contacts at essentially every length scale. And that makes a nucleation length scale a well-defined quantity, because we have that normal stress that is distributed fractally, right? But if for whatever reason you actually go away from that fractal distribution and you just happen to have this patch on the fold which is loaded more, in a sense, it's more abnormal than the rest of the fractally distributed surface, then one could expect deviation. So I'm not saying that that's happening, it's just one possibility.
That's fair.
Thank you.
And Ignacio?
Thank you, Janse. Hi, Greg. Thank you for the great presentation. So actually, I was thinking about exactly the same related with the fractal behavior of the topography, because a few years ago I was working even with Mircea Gregoriu, because I'm from there, from your home, and we were working a lot with synthetic earthquake using random fields with him. We did some models, and last year I started to work with bathymetry. And I could compare, for example, the power spectral densities of the bathymetry and the slip distribution, or the empirical slip distribution coming from inversions. And you can see that the slopes are super similar. Basically, the fractal dimension is very similar between topography and the empirical slip distribution we have estimated from past earthquakes. So as Yuri was saying, I also think that maybe just the topography, while you are having for example, in a subduction zone, while the topography is subducting, maybe that is defining the heterogeneity or the rugosity, and finally will define what will be your future slip distribution in that region. But then the question is all these friction properties can change something on the properties of the slip? Because I would think that that those properties also have to do something in the resultant earthquake you will have in some place. So yeah, that is the first question. I don't know if you think that if you have this solution just ready, we just have to see the topography and we can say something about the earthquake in a certain region. What do you think?
Yeah, I mean, I think there's a lot of things we would like to know about the subsurface, and the topography of a fault is one of them, pretty high on the list. I'd say just the overall stress on the fault is another one. Yeah, I don't know if I can add much to your comment, Ignacio.
Okay. Yeah, and the other thing, this is the last question, is related, or is just a comment related with your spectrum that you are obtaining for the slow sleep and the normal sleep, or the regular sleep. Actually, I was doing also some experiment just using numerical models and started to play with the heterogeneity of the sleep. And I saw that actually the heterogeneity of the sleep in the simulation is not generating any effect of the spectrum. But the temporal aspect of the rupture is basically defining what is happening with the spectrum and when you are having the -1 or the -2. So yeah, it makes a lot of sense to me. Yeah. Thank you, Greg.
Okay, maybe we'll let Xiaohua ask the last question. Xiaohua?
Thanks, Tianze. Hey, Greg, really nice talk. So you showed us a lot of these pink-purple diagrams, which is really great. But my question is that seems to me like all the places you have the nucleation have slow slip events. Is that really the case, or is some design of the experiment or anything related? Yeah.
Yeah, right. So some parts of the fault are like more prone to slow slip than others. The ends of the fault are high. The normal stress is higher at the ends than it is in the center, just because of the edge effect. And so you get a lot of more wear material. You can kind of, it's a little hard to see, but there's a lot of gouge that's built up at the ends. And in the center, there's a bit less gouge. So we end up seeing like creep at the ends of the sample. And of course, we often see nucleation either just transitioning from that creep or at the edge of the creeping region and the locked region. Now, what we did is we took the sample out, and we had been doing experiments for a few years, and we took the sample out and we wiped off all the gouge, and we were able to suppress that creep. So we were able to kind of reset the conditions of the fault a little bit. I will show some examples, or I'll show an example. Let's see. So here's my favorite example of we have this sequence of events that are going on, and then we just stop loading it. So this is us increasing the stress. We just hold it for a minute, and then we load it up again. And event number 10 nucleates differently than the others. So you can see that event number 10, like the nucleation length scale is tiny in comparison to these others. So in this case, we didn't have any, at least not measurable creep. It just nucleated. But usually that's not the case. Usually we get nucleation kind of like at the stress concentration that develops between a creeping and a locked section. Hopefully
I agree. Thanks.
All right. So maybe in the interest of time, we'll wrap up here. Let's thank Greg again for his great talk and all the stimulating discussion that it has generated. And next week, we're going to have our Meet Department seminar again, on which Ross Turner and John Orcutt will present their research briefly. I hope everybody will stay tuned for that. Thank you.
Thank you, Greg.
Thanks for having me.
Bye.
Thank you.
See you next week.
Thanks. Nice talk.